Hey everyone, welcome to the next lesson here. Before I get going with the next lesson, I just thought I'd point out that the assignment that's the first page all the time that you're doing and posting. Um, Obviously, you can redo those if you don't get a high enough at the mark that you're hoping for. Get them submitted properly and done properly and submitted, and I'll update the marks for you as we go. There will be sort of a final deadline for these. The plan will be basically when we get to the end of the unit, we'll schedule a test. I think I'm traditionally going to do like 2 weeks out. I know it's a little crazy, but we have to try and give time for people to catch up on things. And so then there's going to be after the test, basically the windows are closed, okay, for submission for these things because they are really to get you learning along the way. So lots of time at the end. Once the final lesson's done, I'll announce it. The test will be scheduled for the deadline for it. And the deadline would go along with these drop boxes closing. Also, to do with these assignments, they're all from a textbook that I have a class copy of that technically could be lent out to students. So the textbook is posted. I want to show you that textbook is posted in the content and in textbook, and it's this one here. Okay, and I do have an additional textbook there for something else we'll do later on, but that's the textbook. So the page references, I'd encourage you to look at the pages prior to the question page that the questions are on, and look over that material and gain additional knowledge beyond what I showed in the class, of course, things like that, or just see things again to reinforce knowledge. The other textbook is here, and we'll use that one later on in the radioactive decay section of the course. All right, so here we go. We're looking at reflection properties of waves and factors affecting the speed of a wave. Okay, so before we get to that, just take a look at those and tell me which ones you think which one's transverse and which one's sort of a weird kind of, digital representation of transverse versus longitudinal waves. So press pause if you need to think about it or whatever. Hopefully you're answering that this one here would be longitudinal because the vibration, the lines move back and forth left to right, and the wave travels left to right. And then this one here, the lines bounce up and down, but the wave still travels left to right. So the vibration is perpendicular to the direction of travel. Okay. So that was just a brief little reminder of things. So for reflection of waves, I have a video here for a fixed end reflection and for a free end reflection. And I probably should have like this, so I'm not giving away the answer before we get to it. But anyways, here we go. So I'm going to turn the volume down because it's terrible sound quality on the video. I'll just narrate myself here live with the better microphone. And so I'm going to be sending a pulse down on the right side, pulse of a wave or whatever, and then we're going to see how it comes back. So I'll get to the spot here, and I'm going to play it 13 seconds. I'm going to make a mark. Remember that. So there's a pulse, comes back. Okay. And so if I go back to the 13-second mark, we can see it again. Pulse comes back, and so on. Let's slow it down as well. Go to the 13-second mark again. That's good enough. Here's a pulse coming up. Boy, it's very slow. There's a pulse and coming back. Okay, so very obvious looking at that it is coming back out of phase, right? And so basically you have a pulse here on the way in, going like that, and you have the return pulse here on the opposite side coming back, and it's the reflection is out of phase. Okay. Just by observation, you can see that's what's happening. So that is a fixed end reflection. And so on the end here, it's tied, the spring's tied directly to the leg of that table. It can't move back and forth. It's fixed, solid. Okay. The other type is a free end reflection. And so how I do that is I have the spring is actually tied to a string. a super light string, so it's actually tied there and tied here, and it's holding the end of that spring. Okay, so you're going to see here, I'm moving it back and forth to show like it's free to move back and forth. Does that matter? Right? And so we go ahead later here to send the pulse in. I might just put this one in slow motion. I'll play this one full speed. We're starting at 13 seconds again. There we go. I'm consistent at least. Okay, so it's a little too fast to see maybe there. So let's go back to that 13-second mark or so. And let's slow it down. We'll be able to see it. All right, so here we go. Going in, obviously on the right side, and coming back as well on the right side, didn't it? Right? So in on the right side, and obviously back on the right side as well. So with a free end reflection, where it's able to vibrate, able to move at where it's sort of the end of the material, if you will. Obviously, there's still a string there, but it's almost nothing in comparison to the heavy spring. That's considered a free end, and it reflects back out of phase. Let's show that. Okay, so with the fixed end reflection versus the free end reflection. Color code things here a bit. So we have, again, wave like that going there, and wave on the same side coming back, so it reflects in phase. And we'll see this again later, where we have waves traveling from one material to another. And so if a wave is traveling, we're going to look later on at a wave traveling into like a more dense material or to a less dense material, or a material in which the speed changes to a different value. And we're going to see if there's any reflections and properties that we can make sense of. Okay, but for now, that's all we need. So the pictures are like this, right? Where you have a pulse coming in, and with the fixed end coming back out of phase. Okay, so another word for that is a 180-degree phase shift. That's from math class. If you've seen sinusoidal functions yet, if you have a sine function like that, and then I had another sine function. Those are completely in phase, overlapping on each other right now. If I were to shift 180 degrees, which is this mark right here in the middle, because the whole thing repeats after 360 degrees. So this is 180. A phase shift 180 puts you exactly out of phase. And that's what the language is there. If you haven't had grade 11 math yet, you'll see that soon. Yeah, so with a free end reflection, pulse comes back in phase as we saw, so it's drawn like that. So it's a 0-degree phase shift. It's not inverted, however you want to word it. Okay. So that's that. You can press pause, obviously, if you want to slow things down or take notes or whatever. But obviously, I don't need to stop now because you can just press pause. There's just a Google image of the exact same kind of thing. It's tied to a brick wall, so that's a fixed end. And so you'd be able to predict if I had this as a question where this was, covered up. I'd say, hey, what's going to happen? And you'd be able to say, oh, it's going to come back out of phase, okay, based on our knowledge that we saw. And we're not talking about why even right now. Like it's just sometimes we don't necessarily even ask that. Why does it switch phase and so on? So you could, I guess, but it's not something I'm talking about right now. But if you want to talk more about it, we could get a discussion post going to do with it. I think you can see in the video when the pulse gets to the end of this, it's free to go up, and then literally that's just the peak that starts coming back. As it goes back down, the peak travels back. Whereas here, it's not able to go up here like this, and so it strangely goes to the other side. But that's just the way it is. It's what's observed, right? Sometimes it's just, hey, this is what we observe. The idea, actually, I should mention, what we're seeing is very obvious mechanical waves doing something, and then we're going to connect that later on to less easy to analyze waves, like sound waves and light and things like that. All of the things we're learning here will apply later on to, soon, sound waves, and then way more later on, light in grade 12. Right? So pretty critical unit for connecting back to the wave nature, the properties of light later on in grade 12. So the next is factors affecting the speed of a wave. And so let's see if I had just put this video up. So hopefully it's working already. Oh yeah, it is. All right. So here we go for this spring's going to get stretched way out. And let's just jump up to the point here. So I'm going to send a pulse. And so I think the first comparison I'm doing is amplitude. So if you look here in the note, we're saying, okay, does the amplitude, so if I send a small amplitude versus a large amplitude, trying to control the variables, which means I'm only going to change the amplitude. So I would try to make it so the wavelength stays the same, the material is certainly the same, the tension, all other factors are the same other than just the amplitude is the hope, right? If you're trying to see what effect that amplitude has on the speed, you don't want to change a bunch of other things also, because it could have more than one thing changing the speed. So let's go to that. See if it looks like the amplitude one. I don't have the soundtrack going. All right. Okay, so there is. I have to turn the soundtrack on so I know what part of the video I'm at. It's a bit of a longer video. But one that's a long wavelength. Oh, I'm on wavelength. So a big amplitude, basically trying to have the only difference. All right, so here we go. A big amplitude, a little amplitude. There we go. A big amplitude. All right. So trying to control the variables there. We just look at that spot over and over again. Little amplitude. So you could time how long that pulse takes to go there or there and back, whichever. A big amplitude, basically trying to have the only difference. So let's do this again, where we have control variables. So a little amplitude versus. So if we timed from that start to the end, okay, that's a little hard to do because I didn't count it down. So a little amplitude versus a big. Not even like a second and a half though, versus. Amplitude, basically trying to have the only difference between. Right. So if I did this again, I don't think we need to stay on this super long here, but if I did it again and I said, okay, 3, 2, 1 kind of thing, you could actually time it and so on. I find in class what happens is a lot of people guess that the little one is the faster one. And then when we time it, it ends up being the same. And I think people see like the little one as like, I don't know, it's like it's little sneaky pulse versus like the big lumbering pulse or something. But the end result for this is if you go back and watch the video enough times, you could measure it and so on, that the amplitude isn't changing the speed. And I think that could probably kind of make sense too, right? Because you have like the speed of this wave, and as the amplitude dissipates, really it's just the energy of the wave is kind of getting smaller. It's not as much of a deflection from its rest position. But there's not really any reason to believe there's nothing else different, right? There's no real reason to believe that it's not going to transfer through the spring quicker or at a different speed or slower. But your thoughts might vary, of course, but the measurements would be the final answer, and I'll just tell you they end up being the same. The compare is wavelength. So if I had, say, this amplitude, one tile amplitude, but one that's a long wavelength versus. So I'm doing a one tile amplitude as best I can with a short wavelength and a long wavelength. So long wavelength for that one. Before that, there's a shorter wavelength. So we have a short wavelength and a long wavelength. Again, if you test that one, if you were to like rewind this and time how long it takes and so on, you end up seeing one thing I could do actually is slow this down, I suppose. If I put it on slow speed, then it would be a lot easier to sort of see the start of the pulse. Let's see here. But again, the measurements, it's like just a case of whether you want to measure for yourself or believe. So you could start around there, and then, so that's something you could easily do to confirm for yourself that I'm not lying to you, basically, right? So wavelength experimentally doesn't affect the speed as well. And then we go on to back to normal speed for a bit here. There's one I want to do next. a certain tension of the wave. So we had the set tension it was. So we're looking at tension next, and so I'm gathering up the spring in order to get more and more tension. Okay, and then you can see the wave now, and if you time that one, pretty obvious it's going a lot faster. It's taking less time, and I'm gathering up even more impulse, and it's like way under 1 second now, right? So it's just getting faster and faster. And if I was able to lengthen the spring out, like sometimes I'll start with some of the spring already loose in my hand or behind where I'm holding, so I can make it slow, looser tension, less tension as well, and show that it goes slower. But obviously, if tightening it up to higher tension makes it go faster, then the opposite would happen in the opposite way, of course. So tension is affecting the speed. So far, everything wasn't affecting the speed, right? Tension did affect the speed. And then the other one we're looking at is the density. And so for the density one, you'll see that I go and I get a different spring. So in the video, it's a little, I had to go and like tie it to the, or hook it onto the table. Here we go. So this one's a way less dense spring. It's a big old slinky. And the trick is to control variables again, right? So if I just held the slinky as is, it would be a very slow wave, but it's also way less tension to hold, right? And so I gather it up, I keep gathering it up so that it's like even anywhere near the same tension as the other spring. So I gathered up so it's really tightly pulled, but still not as much tension as the other one. So I'm showing the tension's about the same, and then you could time it. And so this one ends up being, if you're anywhere near the same tension, it ends up being faster. And so, the density, right? So yeah, if it's anywhere near the same tension, the lower density makes it be faster. So there are some things we can analyze here as to why. The reflection one, we just kind of said, okay, we're just seeing what it is, right? With the density one, the tension one, let's go to the tension one first. The tension one, I would want you to think of, actually, I may as well go back to these and do this one by one here, but the end result for this one was no, right? It just doesn't. And so I'm not really explaining that one either of these ones at this point. They just, do they affect the speed? No and no. The tension is a little more interesting because it's a yes, right? And so higher tension led to faster wave speed. And so this is a key equation that we're going to be talking about a lot in the course coming up. And so if you have higher tension, you can think of it as the force that's between the coils of the spring is greater, and so it's going to be able to transfer a force, like transfer that through the spring quicker. So it's going to pull on the next coil harder, and so it's going to change its speed quicker. That's exactly what this equation is, which is just force, mass, and acceleration. So that if there's more force, there's more acceleration, right? So if the acceleration from rest to whipping and doing the wave thing is quicker, obviously the wave is going to transfer quicker through the material. That one's very justifiable. And along the same lines, we found the density, right, affected things. So less dense led to faster. And that's actually very justifiable as well, because when you push on lighter things, they speed up quicker than when you push by the same amount on heavy things. Right, so that's an equation. Again, like I said, we're going to analyze that one really nicely in the course later on. So I just have to sort of talk about it a little bit here out of turn, I guess.
This is Claire.
So hopefully the announcement's not too annoying for you there. And so yeah, the idea is it's pulling on the next coil. While if the coils are lighter, it's going to be able to transfer the wave from one coil to the next quicker. It's going to have a faster speed. Okay, so feel free to go look through those videos and do measurements to confirm these things. So I'm not lying to you, but you can trust me. So conclusion is that the speed of the wave material is really determined by the physical properties of the material itself, the density, the tension, things like that. It's not determined by the properties of the wave, like the amplitude, the frequency, the wavelength, things like that. So if I go to a spring, like I'm using here, and I vibrate fast or slow, make a vibration be fast or slow or big or small or whatever, that's just the vibration itself. How that vibration travels through the material depends on what that material is, the characteristics of the material itself, right? So if we're using that knowledge to try and analyze speeds of waves in different substances, the trick is you have competing factors, right? So if you look at water, it's really high density in comparison to air. So you might think, oh, it's way lower speed, right, in comparison to air. Yeah. But there's a competing factor here where the cohesion between the molecules is kind of like an analogy to the tension in the spring, right? It's a good physical way to think of the cohesion between the molecules. And in water, that's way higher, right? And so if this is the bigger factor in determining the speed, then that would lead to the speed of sound in water being faster, which is actually the case. All right. So these these competing factors, I'll show you here the speeds in water. The speed in meters per second is 1,433 versus in air it's around 300 or 400 or whatever. Yeah, 340. I have it listed in. We'll see an equation to do with that soon based on temperature. Okay, so all these different materials, you could start to think it through, right? Like picturing say the speed in lead in comparison to steel. It makes sense that steel is a heck of a lot faster because lead's very soft, right? So the tension between them is low, plus it's very dense. So both factors lead to lead having a lower speed of sound in it than a slower speed of sound than steel. Okay, but again, those competing factors sometimes can be in the opposite direction. It makes it a little harder to picture or predict, I should say. Another factor that to consider, water in terms of water waves is the depth. So this is actually just a screenshot of a video to do with the water waves, and I'm not even going to click on the video because it's kind of hard to see the speed in anyways. But basically, little ripples are being made, and you'll learn a lot more about this later on. Actually, you would have seen it in grade 10, I suppose. So, but the little ripple forms like a lens and focuses, and so you can see the waves. And so basically these waves are farther apart because there's a bar here that's making ripples at the same time. It's actually up here, I guess. It's making ripples in with a certain frequency all the way across. And then those waves are traveling slow here, makes the wavelength it doesn't travel as far between oscillations of the paddle that's across here. And then this one, of course, is going faster, right? So this is the deeper water where waves go faster. This is the slower water, and that'll come in to play later on in a neat thing when we look at how waves behave at the beach. So yeah, that's it for today. There's your questions to do with it. This one just says to go view page width here for you. This one just shows to draw the reflection. So just fill in what the spring would look like, right, from a fixed end or a free end. So I have a free end there, and I threw an anchor on there to show that it's like a fixed end. I was going to either do an anchor or a brick wall, and the anchor was kind of easiest to, hopefully that's obvious what I mean. It's locked in place. Yeah, just there you go. There's what you want to complete and submit and ask questions about if you need help. All right. Hope everything's going well. Let me know if you need anything. Talk to you later.